Okay. By the way, you know, like for example, on a constant current source like this is a constant current sink, but basically it regulates itself by, this part of it is very reminiscent of power supply overcurrent protection circuits you sometimes see. So basically, it's looking at the voltage formed across this 330 ohm resistor, and when it's approximately 0.65 volts, that's its limit. So, and that's determined by what current has got going through it. In this case, you have about 2 milliamps going through that. That's going to equal approximately the diode voltage drop across this transistor, so it'll start to conduct if it sees that kind of current on it. All right, and basically, this resistor here is just kind of a dummy load as to, dump excess current into it. It has some effect on the current, but overall, it's pretty independent of that. It's this element that actually is primarily responsible for setting the current. Now, how it works is that, this collector voltage, can vary, right? It's a transistor, so it can vary its resistance. Trans resistor, is what a transistor kind of stands for. So, it's a dynamic resistance. That's the way to kind of look at it. It's one way to look at it. But when this voltage, gets high enough, and you understand when you first turn the circuit on, basically this transistor Q2 is off, but current will actually flow through this transistor's diode from this 10K resistor and through this resistor and start causing the voltage to increase, right, as the power supply comes on. But eventually it'll reach a point, okay, to where it's reached that diode voltage drop across that resistor. When it does, it'll start altering its voltage. It'll start increasing or decreasing its voltage to starve Q2, in an attempt to starve Q2 as current, of current, because Q2, when the thing is first turning on, does start to conduct current through it, just because it's got a base current and it's doing its transistor thing, trying to drive a current through your load. Now, if you don't have a load connected, it's just going to see the diode, right? But still, the same thing's going to happen. It's still going to actually start starving this transistor of its voltage in order to try to reduce current. So instead of it being like 0.7 volts, let's say it was at 0.8 volts, well, it's going to decrease that voltage on its collector in order to starve current from this transistor, so that it reduces the voltage drop across the resistor. That's how it works. And it's a very simple principle, but that in effect ends up controlling the current through this too. So the current going through this resistor is going to be almost identical to the current going through your load. So, because that's what the transistor is dealing with, its collector and emitter curves have to be about the same, with the discrepancy of the voltage, any current, due to the base, of course. So there'll be a slight difference due to the base current, but overall, that's how it works. It's self-balancing, and the same thing kind of applies to the FET. You've got the same transistor circuit here doing the same thing. This is still responsible for setting the current, but instead of starving it of current like it's doing over here, it's starving it of voltage. So it actually tends to regulate the voltage of the FET, which causes the current to either increase or decrease. So it's able to adjust itself to do that as well. So that's what's interesting about bipolar transistors. They're real versatile because they can actually operate on a current control device or a voltage control device with the same effect. So pretty much. So, but that's basically how these constant current sources work. If you're wondering, you can kind of fuck around on Fallstat and figure that out for yourself probably. But I did have one other thing I wanted to say, on the current mirror thing. It occurred to me that, okay, basically the current on this side controls the current on that side, right? Well, it occurred to me that, if you had, like, let's say, I don't know, because again, like I've demonstrated on the FET circuit, the voltage on your control transistor doesn't have to be the same as the voltage on your load transistor, right? So in theory, you could actually detach R1 here and tie it to a different voltage source, like say the output of a unity gain op amp, right? and that can handle 20 or 30 milliamps, whatever current you wanted to allow through this thing. And you might want to put a resistor. Goddamn flying ant fuckers! Goddamn little motherfuckers! But yeah, you might be able to use an op amp, put a little like 3.3K resistor in it, like I did my circuit, but and then have that set up as a unity gain non-inverting amplifier, and have a DAC hooked to that, so you could actually make a computer controlled constant current source, because this still acts like a constant current source. And I would imagine one of these more elaborate ones down here may even do a better job. So that's just food for thought if you needed an actual current controlled a computer controlled constant current source that operates at a substantial voltage. Because again, if you use high voltage transistors in here, there's no reason this thing couldn't operate at 100 volts or more. Again, keep in mind, your current and safe operating area on your transistors. If you're dissipating more than 1 or 2 milliamps over a large voltage, you got to take the power handling capabilities into account, of course. But the point is, you could do it, and make a current sink or source, because these things I think can work in reverse. I think you can make them source mirrors as well as sink mirrors, like this is a current sink, because I'm pretty sure I've seen them that way. And if you look at the circuit diagrams of op amps, and so forth in data sheets, you can kind of see interesting things in there. That's what's good, about a couple of these books, is they talk about things like that. Like how the what the internal circuitry on some of that stuff does. So it's rather interesting. I think Malvino does a better job on that, than Hazen did. But if I recall correctly, but I'll find out here shortly to refresh my memory on it. But at any rate, I just wanted to throw that in there as a last minute little tidbit. So, cheers.